Imagine standing on the edge of space and time, watching as two galaxies, each containing billions of stars, slam into one another in a dazzling display of cosmic chaos. Colossal explosions ripple across the void, sending shockwaves through the fabric of reality itself. This isn't science fiction. This is the universe's grand story, written in collisions so powerful they shaped everything we see today. From the birth of planets to the formation of galaxies, our cosmos has been forged in moments of unimaginable violence, and you're about to witness 25 of the most monumental impacts that changed the course of cosmic history forever. Think of the universe as a vast, ever-changing battlefield where titanic forces collide. These aren't just random accidents, they're the architects of existence. When galaxies merge, they don't just drift together gently. They tear each other apart, warp space-time, and ignite the birth of new stars in fiery cascades. When asteroids strike planets, they don't just leave craters. They can wipe out entire species or even deliver the building blocks of life itself. Every cataclysm, every explosion, every shattering impact has left its mark on the cosmos, steering its evolution in ways we're only beginning to understand. This journey isn't just about destruction, it's about creation. The same collisions that bring chaos also spark new beginnings. Without them, Earth might never have formed. The moon might not exist. Life as we know it could be completely different or non-existent. So buckle up, because we're traveling billions of years into the past across unimaginable distances to witness the most pivotal moments in the universe's history. From the asteroid that ended the dinosaurs to the galactic mergers that shaped the Milky Way, these collisions didn't just change the universe, they made it what it is today. And by the end, you'll see the cosmos in a way you never have before. Long before galaxies or planets existed, before even time itself had meaning, the universe began with the most colossal collision of all, the Big Bang. But forget what you've heard about it being just a fiery explosion. This was the original cosmic collision, an event so immense it didn't just create matter and energy, it birthed reality as we know it. Picture this, an unfathomable concentration of energy, hotter and denser than anything in existence today, suddenly expanding faster than light, forging the very fabric of space and time in its wake. Scientists now believe the Big Bang might not have been a singular event but the aftermath of something even more extraordinary. One leading theory suggests our universe was born from a collision between two higher dimensional membranes, or brains, floating in a vast multiverse. Imagine two sheets of paper slamming together in an unseen dimension, releasing enough energy to spark an entire cosmos. This is the heart of M-theory, where our universe is just one bubble in an endless froth of parallel realities. What makes this collision truly staggering is its aftermath. Within the first second, temperatures soared to 100 billion degrees, fusing particles into existence so rapidly that matter and antimatter nearly annihilated each other. A slight asymmetry, just one extra particle of matter for every billion antimatter particles left behind the building blocks of everything we see today. Without that imbalance, stars, planets, and life itself would never have formed. The echoes of this collision still surround us. The cosmic microwave background, a faint glow permeating space, is the cooled remnant of that primordial fireball, a snapshot of the universe when it was just 380,000 years old. Even now, telescopes like the James Webb Space Telescope are peering deeper into this radiation, hunting for clues about what truly triggered the universe into being. So when you look up at the night sky, remember, you're witnessing the aftermath of the greatest collision of all time. Billions of years after the Big Bang, while the universe was still shaping its grand structures, a quieter but no less revolutionary collision was unfolding right here on Earth, one that didn't involve asteroids or galaxies, but something far smaller and yet infinitely more transformative: microscopic cyanobacteria. These tiny organisms were about to trigger a catastrophe that would rewrite the rules of life itself, the Great Oxygenation Event. At first glance, it's hard to imagine something as delicate as bacteria causing a planetary-scale disaster. But picture Earth 3.5 billion years ago, a world of smoldering volcanoes, toxic gases, and vast oceans simmering under a dim, hazy sky. Life existed, but only in its simplest forms, single-celled microbes thriving in the absence of oxygen. Then came cyanobacteria, the first organisms to unlock the power of photosynthesis. They began absorbing sunlight, exhaling oxygen as waste, a gas so reactive it was essentially poison to most early life. This was no gentle transition. Oxygen flooded the oceans first, rusting dissolved iron and turning the sea's blood red with iron oxide before sinking to the seafloor in thick layers we still mine today. Then it invaded the atmosphere, reacting violently with methane, a greenhouse gas that had kept the planet warm. As methane levels plummeted, Earth plunged into its first ice age, a global deep freeze so extreme scientists call it Snowball Earth. Entire ecosystems collapsed. Anaerobic life, unprepared for this toxic new world, perished in what may have been the first mass extinction. Yet from this devastation emerged an opportunity. Oxygen's reactivity wasn't just destructive, it was a powerhouse of energy. Over millions of years, some organisms evolved to harness it, unlocking 16 times more energy than fermentation. This energy surplus paved the way for complex cells, then multicellular life, and eventually every plant, animal, and human that would follow. Without that ancient bacterial collision with chemistry, our cells bursting with mitochondria, the descendants of oxygen-breathing microbes, would never have existed. Even now, we're living in the aftermath, the rusted bands in ancient rocks, the oxygen in your lungs right now. The very fact that fire exists all trace back to this microscopic revolution. It's a reminder that sometimes the most earth-shattering collisions don't come from the cosmos, but from the quiet persistence of life itself. 4.5 billion years ago, when our solar system was just a swirling chaos of dust and debris, two young worlds found themselves on a fatal collision course. Earth, still a molten, half-formed planet, was about to meet Theia, a Mars-sized protoplanet streaking through space. This wasn't just another cosmic crash. This impact would sculpt our world in ways we're still discovering today, leaving behind not just debris but an entirely new celestial body, our moon. Recent analysis of lunar rocks reveals something astonishing. The moon isn't just a chunk of Earth or Theia. It's a scrambled mix of both. When Theia struck at over 40,000 kilometers per hour, the energy was so immense that both worlds effectively liquefied, their cores merging while a colossal spray of vaporized rock was flung into orbit. That swirling disk of superheated material gradually coalesced under gravity, forming a glowing new world in our skies. Without this collision, nights on Earth would be pitch black, tides would barely exist, and life as we know it might never have gained a foothold. But the Theia impact did more than create the moon. It fundamentally altered Earth's destiny. The sheer force of the collision knocked our planet off its axis, tilting it 23.5 degrees. That tilt gives us seasons, the rhythmic dance of winter, spring, summer, and fall that shapes ecosystems across the globe. It also stabilized Earth's rotation, preventing the chaotic wobbles that make other planets like Mars experience wild climate swings over millennia. Perhaps most remarkably, the moon acts as Earth's silent guardian. Its gravitational pull slows our planet's rotation from what was once a dizzying 6-hour day to the 24-hour rhythm we know today. Without that stabilizing influence, winds would howl at hurricane speeds, and day-night temperature extremes could make complex life impossible. Even now, the moon continues to drift away at nearly 4 centimeters per year, a living testament to that ancient world-shaping collision. Hidden within lunar dust are clues that could rewrite our understanding of this event. Some scientists now believe Theia's impact may have delivered water to early Earth, locked within minerals that survived the cataclysm. Others speculate that fragments of Theia's core might still exist deep within our planet, potentially explaining mysterious dense zones in Earth's mantle detected by seismic waves. Every new moon rock analyzed, every computer simulation refined, brings us closer to reliving that moment when two worlds became one, and in doing so made life on Earth possible. The early Earth wasn't just shaped by one or two colossal impacts, it endured a relentless storm of destruction unlike anything in recorded history. 4 billion years ago, long after the moon had formed and the planet's crust had cooled, our solar system descended into chaos. A colossal gravitational dance between Jupiter and Saturn destabilized the orbits of countless asteroids and icy comets, flinging them inward like cosmic bullets. For nearly 200 million years, Earth and its neighboring planets were caught in the crossfire of what scientists call the Late Heavy Bombardment, a period so violent it left scars we can still see today. Look at the moon's pockmarked surface through a telescope, and you're glimpsing a time when impacts weren't rare events but a daily catastrophe. Craters like the 1,600-kilometer-wide Imbrium Basin weren't formed by gentle nudges. They were carved by asteroids larger than cities, striking with enough force to vaporize rock and send tidal waves of molten debris rippling across the young Earth. These collisions were so frequent that some models suggest the planet's surface effectively resurfaced itself every few thousand years, erasing entire landscapes under layers of searing hot ejecta. Yet hidden in this apocalypse was a paradox. The very violence that threatened to sterilize Earth may have planted the seeds for life. Many of those incoming projectiles weren't just barren rocks. They were icy comets, rich with frozen water and organic molecules like amino acids. When they slammed into Earth's steamy atmosphere, they didn't just explode, they cracked open, releasing their precious cargo. Over time, these impacts could have delivered enough water to fill Earth's oceans, turning what was once a dry, hostile world into a shimmering blue cradle. Some of the oldest minerals on Earth, zircon crystals dating back 4.4 billion years, tell a tantalizing story. Trapped within them are chemical signatures suggesting liquid water existed even during the bombardment's peak. That means life's ingredients, water, organic compounds, and energy from volcanic vents were all present in the chaos. It's a haunting thought. The same impacts that turned the planet's surface into a hellscape may have simultaneously filled its oceans and laced them with the building blocks of DNA. But the bombardment didn't just gift Earth with water. It shaped its very geology. The relentless pounding likely triggered massive volcanic eruptions, releasing gases that thickened the atmosphere and stabilized the climate. Some researchers even argue that the energy from these impacts could have jump-started chemical reactions in primordial pools, accelerating the formation of complex molecules. Today, we're still uncovering clues about this turbulent era. Missions like NASA OSIRIS-REx, which retrieved samples from the asteroid Bennu, reveal just how carbon-rich these ancient space rocks truly are. Meanwhile, lab experiments show that when simulated comet ice is blasted with impact energy, it can form not just amino acids but even the nucleobases found in RNA. The line between destruction and creation, it seems, was always thinner than we imagined. So the next time you sip a glass of water or feel the warmth of sunlight, remember, you might owe your existence to the most violent chapter in Earth's history. 66 million years ago, as dinosaurs roamed the lush landscapes of what we now call Mexico's Yucatan Peninsula, a city-sized asteroid wider than Mount Everest is tall, streaked through Earth's atmosphere at 20 times the speed of a bullet. In the last moments before impact, the sky would have ignited into an incandescent wall of fire, casting shadows thousands of miles across the planet. Then, in a fraction of a second, 10 billion atomic bombs worth of energy detonated on contact, vaporizing rock, water, and life instantly. This was the Chicxulub impact, the most consequential collision in Earth's history since the birth of the Moon, and its aftermath didn't just wipe out the dinosaurs. It rewrote the rules of life itself. Recent discoveries have pinpointed the catastrophe to springtime in the Northern Hemisphere, a detail uncovered by analyzing ancient fish fossils from the exact day of impact. These fossils, found in North Dakota over 3,000 kilometers from the crater, capture the moment debris began raining down globally. Their gills are clogged with tiny glass beads. Tektites formed when the asteroid vaporized bedrock and flung molten droplets skyward at escape velocity. But the real horror began after the initial firestorm. The impact ignited wildfires across continents, but it was what came next that turned the event into a multi-decade apocalypse. Sulfurous gases from vaporized limestone mixed with soot from burning forests, forming a global shroud so thick it blocked 90% of sunlight. Photosynthesis ground to a halt, collapsing food chains from the bottom up. Temperatures plummeted by nearly 30 degrees Celsius, a volcanic winter lasting up to 30 years. Acid rain turned oceans corrosive, dissolving the shells of plankton that form the base of marine ecosystems. Even creatures that survived the initial cataclysm faced a slow, grinding extinction as starvation and climate chaos rippled through every habitat. Yet hidden in this devastation was an opening, one that mammals, until then small, burrowing creatures, seized upon. With dinosaurs gone and ecological niches vacant, these survivors diversified explosively. Without Chicxulub, primates might never have evolved into tool users, and humans wouldn't exist. The irony is staggering. The same impact that erased 75% of species also cleared the path for our ancestors' rise. Modern simulations reveal even darker details. The asteroid struck at the worst possible angle, 20 to 30 degrees, maximizing the amount of debris hurled into the upper atmosphere. Had it hit hours earlier or later, it might have landed in deep ocean, dissipating much of its energy harmlessly. Instead, it struck shallow waters, vaporizing sulfur-rich seabeds and guaranteeing a climate catastrophe. Today, the crater itself tells a story of rebirth. Core samples from its peak ring, a circular mountain range within the impact zone, show microbial life colonized the fractured rock within years, thriving in the scalding, mineral-rich fractures. It's a testament to life's tenacity. Even in the wake of cosmic violence, it finds a way. The dinosaurs' tragedy became our genesis, written in the scars of a 6-mile-wide rock from the heavens. Jupiter, the solar system's largest planet, might owe its existence to a series of violent crashes that reshaped its core in ways we're only beginning to understand. Deep beneath its swirling bands of gas lies a mystery, a dense, rocky core twice as massive as Earth, wrapped in layers of metallic hydrogen. But how did this colossal structure form? One groundbreaking theory suggests it wasn't built gently from dust and ice, but forged in the furnace of protoplanetary collisions so powerful they vaporized entire worlds. Picture the early solar system 4.5 billion years ago, a chaotic construction zone where dozens of fledgling planets, or planetesimals, jostled for space. Jupiter's birthplace was especially crowded, its gravity pulling in nearby objects like a cosmic vacuum cleaner. According to computer simulations, some of these objects weren't just absorbed, they slammed into Jupiter's growing core at speeds exceeding 60,000 kilometers per hour. The energy released would have been staggering, heating the core to temperatures rivaling the sun's surface and melting heavy elements like iron and nickel into a swirling, liquid metal ocean. These collisions didn't just add mass, they fundamentally altered Jupiter's chemistry. When a Mars-sized protoplanet collided with the young Jupiter, the impact could have blasted away lighter elements like hydrogen and helium from the core region, leaving behind a concentrated mix of heavier materials. This might explain why Jupiter's core is denser than expected, a puzzle that baffled scientists until a collision theory emerged. Even more remarkably, Some models suggest these impacts stirred the core so violently that they disrupted its original structure, creating the strange, fuzzy, or partially diluted core we detect today through gravitational measurements. The echoes of these ancient crashes still ripple through Jupiter's atmosphere. The planet's intense magnetic field, 20,000 times stronger than Earth's, likely draws its power from the turbulent motions of that metallic hydrogen layer, a direct consequence of the core's violent formation. Recent data from NASA's Juno spacecraft revealed another clue. Jupiter's gravitational field is lopsided, with more mass concentrated in the northern hemisphere. This asymmetry could be the ghostly fingerprint of a gargantuan impact that reshaped the core billions of years ago, but the collisions didn't stop there. Some astronomers propose that Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, might be surviving fragments of the protoplanets that failed to merge with the core. Io's spectacular volcanism and Europa's subsurface ocean could be remnants of the heat and water delivered during these primordial collisions. Even Jupiter's bizarre auroras, which blaze with X-rays near its poles, might trace back to particles trapped in a magnetic field sculpted by its cataclysmic youth. What makes this discovery revolutionary is its implication for exoplanets. If gas giants commonly form through violent mergers, it could explain why so many alien worlds defy our expectations, like hot Jupiters with oddly small cores or puffy planets with extended atmospheres. Every time we peer deeper into Jupiter's stormy heart, we're glimpsing the aftermath of a demolition derby that shaped not just one planet, but the architecture of our entire solar system. Right now, two cosmic giants, our Milky Way and the Andromeda galaxy, are hurtling toward each other at 300,000 kilometers per hour, locked in a gravitational embrace that began billions of years ago. This isn't a hypothetical scenario, it's an inevitable future written in the trajectories of stars, measured with pinpoint precision by the Hubble Space Telescope. When these spiral galaxies collide 4 billion years from now, the night sky will transform in ways no human eyes will witness, but we can imagine the spectacle. First, forget everything you've seen in animations where galaxies smash like cars in a cosmic fender bender. Space is so vast that individual stars rarely collide. Instead, they'll slide past one another like swirling dancers, guided by gravity's invisible hand. Over hundreds of millions of years, the Milky Way's signature spiral arms will stretch and warp, pulled apart by Andromeda's immense tidal forces. Gas clouds compressed in the chaos will ignite blue-hot bursts of new stars, while ancient red giants glow like embers in the celestial storm. Hubble's observations reveal Andromeda isn't coming straight for us, it's slightly off-center, guaranteeing a sideswipe before a second pass finally merges the galaxies into one. Earth's fate hinges on chance. If our solar system gets flung outward, we might orbit the new galaxy's outskirts, bathed in the eerie glow of colliding gas clouds. If we're drawn toward the core, the night sky could become a blazing tapestry of stars, so densely packed that constellations become unrecognizable and darkness never fully falls. The end result, a colossal elliptical galaxy astronomers dub Milkomda, its stars orbiting a shared center in slow, stately loops, yet even this won't be the final act. Simulations suggest the merged galaxy might later collide with the Triangulum galaxy, continuing the universe's endless dance of destruction and rebirth. The most humbling realization, this collision has already begun. The light we see from Andromeda tonight is a snapshot from 2.5 million years ago, a prelude to a future where galaxies unite. Deep in the constellation Carina, two galaxy clusters, each containing hundreds of galaxies, slammed into one another at mind-bending speeds, creating one of the most revealing cosmic accidents ever observed, the Bullet Cluster. But what makes this collision extraordinary isn't just the spectacle, it's the invisible wreckage left behind. When astronomers first studied this system, they found something that shouldn't have been possible. The visible matter, glowing hot gas detected by X-ray telescopes, wasn't where the gravity was. Stars from both clusters had sailed right past each other, while the gas, slowed by friction, lagged behind. But here's the puzzle: the gravitational lensing effect, which bends light from distant background galaxies, revealed most of the cluster's mass wasn't with the stars or the gas. It was somewhere else entirely. This mismatch became smoking gun evidence for dark matter. Think of it like a ghostly traffic collision where only the paint smears are visible. You'd see colorful streaks on the asphalt, but the cars themselves, weighing tons, would be completely transparent. In the bullet cluster, the paint smears are the hot gas clouds visible in X-rays, while the invisible cars are the dark matter halos, detectable only by how they warp spacetime. The collision literally ripped ordinary matter apart from the unseen stuff, proving dark matter isn't just a mathematical fudge, it's a physical substance that doesn't interact with light but dominates the cosmos's mass. Detailed measurements reveal even stranger details. The gas clouds, heated to millions of degrees during the impact, created shock waves resembling cosmic bullet trails. Meanwhile, dark matter, unaffected by electromagnetic forces, passed through the chaos unscathed, leaving gravity to map its distribution like an unseen shadow. Even now, computer simulations struggle to replicate the precise separation between the visible and invisible components, hinting at properties of dark matter we still don't fully grasp. The bullet cluster isn't alone. Similar collisions like the musket ball cluster and El Gordo show the same eerie separation. Each one reinforces a startling truth. What we call normal matter planets, stars, even our own bodies, makes up less than 5% of the universe's total content. The rest is a mystery, its presence inferred only through the wake it leaves in the fabric of reality. What's next? Astronomers are hunting for dark galaxies, structures rich in dark matter but nearly devoid of stars, that could reveal how this enigmatic substance behaves in isolation. Others are studying collisions at different angles to see if dark matter exhibits even faint interactions beyond gravity. Every new cluster crash is like a high-energy physics experiment written across millions of light-years, offering clues to the universe's hidden architecture. So the next time you hear someone question whether dark matter is real, point them to the bullet cluster where the unseeable left its signature in the stars. On a crisp November night in 1572, as Danish nobleman Tycho Brahe strolled through his uncle's garden, a blinding new star erupted in the constellation Cassiopeia, so bright it outshone Venus and became visible even in daylight for weeks. This wasn't just a new celestial object, it was a cataclysm 4,500 light-years away, a white dwarf star stealing matter from a companion until the stolen gas ignited a thermonuclear fireball, tearing the star apart in what we now call a Type Ia supernova. But its true impact wasn't just in the sky. It shattered a 1,600-year-old dogma, Aristotle's claim that the heavens were perfect and unchanging. At the time, European scholars clung to Aristotle's cosmology like gospel. Stars were fixed on crystalline spheres, they believed, beyond the corruptible realm of Earth. Comets and meteors, mere atmospheric disturbances like clouds. Then came Tycho's supernova, persisting for 18 months, stubbornly refusing to fade or move like a comet should. Using rudimentary instruments, Tycho measured its parallax, proving it lay far beyond the moon. His data struck the first blow to Aristotle's model, paving the way for Kepler's laws and Newton's gravity. Modern telescopes reveal the debris field still expanding at 5,000 kilometers per second, a tattered veil of silicon, iron, and radioactive titanium flung outward by the explosion. But here's what Tycho couldn't have known. That supernova was a cosmic alchemist. The fury of its collapse forged elements like gold and uranium, the very atoms in your jewelry and phone. Even more astonishing, the explosion's light may have reached Earth just as Galileo was born, as if the universe itself timed a revolution. The aftermath still holds mysteries. In 2008, astronomers found a surviving star near the blast's epicenter, likely the donor that fed the white dwarf until it detonated. Its helium-rich atmosphere, stripped by the explosion, is now a forensic clue to the binary system's final moments. Meanwhile, X-ray observatories detect arcs of shock waves rippling through interstellar space, accelerating particles to near light speed. Tycho's supernova didn't just change astronomy, it redefined humanity's place in the cosmos. Before 1572, the heavens were static, distant, and divine. Afterward, they became dynamic, violent, and knowable. Every time a modern astronomer measures the expansion of the universe using supernova as mileposts, they're standing on the shoulders of a star that refused to be ignored. Somewhere in the vast cosmic void, hidden behind the dense stars of our Milky Way's disk, an unseen force is pulling thousands of galaxies, including our own, toward it at breakneck speeds. Astronomers call this enigma the Great Attractor, a gravitational anomaly so powerful it bends the motion of entire galaxy clusters like a cosmic puppeteer. Imagine floating in a river where the water flows not downhill, but toward some invisible drain. That's the unsettling mystery scientists face when mapping the trajectories of nearby galaxies. The first clues emerged in the 1970s when astronomers noticed something bizarre. All galaxies in our local supercluster, including the Milky Way, are streaming toward a single point in space near the constellation Centaurus at roughly 2 million kilometers per hour. At first, researchers assumed it was just the pull of known galaxy clusters like Norma. But when they added up the mass of every visible structure in that direction, the numbers didn't come close to explaining the tremendous gravitational tug. Something colossal, 6 times more massive than the entire Virgo supercluster, had to be lurking there, invisible to our telescopes. What makes this region so hard to study? Our own galaxy blocks the view. The Great Attractor lies in what astronomers call the zone of avoidance, an area of the sky obscured by the Milky Way's dust and stars. It's like trying to spot a lighthouse through a blizzard, but modern technology is peeling back the veil. X-ray telescopes like Chandra have pierced the galactic fog, revealing a concentration of galaxy clusters so dense they form a supercluster of superclusters, dubbed Laniakea Hawaiian for immeasurable heaven. This structure, spanning 500 million light-years, may be the true source of the Great Attractor's pull, yet even Laniakea might just be part of something grander. Some theorists suggest the Great Attractor could be a focal point where multiple galactic filaments, the largest known structures in the universe, converge, creating a gravitational well that draws in everything around it. Others speculate it's the aftermath of an ancient collision between galaxy clusters so massive it warped spacetime itself, the most mind-bending theory. The Great Attractor might not be the final destination. Our local galaxies could be caught in a far larger current, pulled toward an even more massive structure called the Shapley supercluster, 800 million light-years away. It's a cosmic wake-up call. No matter how vast our corner of the universe seems, we're still just leaves floating in a stream whose source we've yet to find. Every new observation deepens the mystery. Radio telescopes mapping hydrogen gas have found entire galaxies moving in sync like schools of fish, their paths tracing the gravitational web we're only beginning to map. Meanwhile, dark matter simulations suggest such attractors might be common knots in the cosmic net where invisible threads of dark matter intersect. So when you look toward Centaurus, remember, out there in the darkness, something we can't see is pulling us inexorably forward, a reminder that even in an expanding universe, gravity's embrace never lets go. Far beyond the orbit of Neptune, in the frigid outskirts of our solar system, lies a cosmic demolition derby frozen in time, the Kuiper Belt. This vast ring of icy remnants might seem tranquil today, but 4 billion years ago, it was ground zero for a gravitational upheaval that reshaped the outer solar system. The instigator, Neptune, the solar system's blue giant, whose migration through this region sent countless icy bodies careening like billiard balls in a celestial break shot. As Neptune slowly spiraled outward after its formation, its immense gravity became a wrecking ball, disturbing the orbits of primordial ice dwarfs and flinging them in all directions. Some were hurled inward, becoming short-period comets like Halley's, those dazzling visitors that streak across our skies every few decades. Others were ejected entirely, cast into the Oort cloud or interstellar space. But the most fascinating victims were those trapped in orbital resonances with Neptune, forced into elongated paths that kept them perpetually out of reach. Pluto, with its tilted, elliptical orbit, is the most famous prisoner of this cosmic reshuffling, a rebel world whose very existence hints at the chaos of the early solar system. The scars of this migration are everywhere. Recent simulations show that Neptune's journey wasn't smooth. It was punctuated by violent gravitational tugs of war with Jupiter and Saturn, creating bursts of instability that sent shockwaves through the Kuiper belt. Imagine a snowplow barreling through a field of delicate frost, its blade kicking up ice crystals in chaotic swirls. That's essentially what Neptune did, leaving behind a scattered disk of objects with wildly inclined orbits and a faint kernel of undisturbed bodies that avoided the turmoil. Today, astronomers study these icy fossils to decode the solar system's history. The Kuiper belt's population is oddly divided clustered groups like the Plutinos, which share Pluto's three resonance with Neptune, and hot classical objects with steep orbital tilts, all telling different chapters of the same story. Even more telling are the blueberries of the Kuiper belt objects like Arakoth, the snowman-shaped world visited by NAS, A New Horizons. Its undisturbed binary shape suggests it formed peacefully before being flung outward, a time capsule from an era before the Great Scattering. But the Kuiper belt isn't just a museum, it's still active. Collisions between these icy bodies occur far more often than we once thought, creating faint clouds of debris and possibly even triggering short-lived atmospheres on dwarf planets like Makemake. Some researchers speculate that Neptune's migration could have shepherded a lost fifth giant planet out of the solar system entirely, leaving behind only subtle clues in the orbital patterns of distant objects. Every new discovery, from bizarre binary systems to oddly colored surfaces, adds another piece to the puzzle of how gravity's fingerprint shaped the solar system's final frontier. What's truly humbling is realizing that Earth's water, and perhaps even the organic ingredients for life, might trace back to this violent reshuffling. As Neptune plowed through the Kuiper belt's precursor, it likely redirected water-rich comets toward the inner solar system, delivering them to young planets like ours. So the next time you sip a glass of water or gaze at a comet's tail, remember, you're witnessing the aftermath of a gravitational upheaval that began 4 billion years ago, when a wandering giant turned order into chaos and chaos into the building blocks of life. Could Mars hold the scars of an ancient cataclysmic collision, one that reshaped not just the red planet but may have set the stage for Earth's moon to form? A bold new theory suggests Theia, the same Mars-sized protoplanet thought to have birthed our moon, first struck Mars in a glancing blow before continuing its fateful journey toward Earth. If true, this would solve two cosmic mysteries at once: why Mars looks so lopsided and why lunar rocks carry chemical signatures unlike anything in Earth's mantle. The evidence starts with Mars itself. Look at a topographic map of the planet and you'll notice something striking: a stark division between hemispheres. The northern lowlands are smooth and flat, stretching 4 kilometers lower than the southern highlands with their battered, ancient terrain. This Martian dichotomy has puzzled scientists for decades. Some proposed asteroid impacts, but none matched the scale, until researchers ran simulations of Theia sideswiping Mars at a shallow angle. The results were startling. At roughly 15 kilometers per second, Theia's gravity could have ripped away a portion of Mars' northern crust while simultaneously tilting the planet's axis by 20 degrees, explaining both the dichotomy and Mars' present-day axial tilt in one colossal event. Here's where the Moon connection gets fascinating. If Theia first scraped past Mars, it would have collected a veneer of Martian crust before continuing toward Earth. When it later collided with our planet, that extra material would have mixed into the debris disk that formed the Moon. This could finally explain why Apollo mission samples revealed lunar rocks with isotopic ratios subtly different from Earth's, an anomaly scientists call the lunar compositional crisis. The Moon might not just be Earth and Theia's offspring, but a cosmic cocktail with traces of Mars stirred in. Skeptics point out hurdles. Mars' crust today shows no clear isotopic signature matching the Moon, though proponents counter that Theia likely stripped material now lost to space. Others argue Mars' dichotomy could stem from internal processes like mantle plumes melting one hemisphere. Yet new clues keep emerging. Mars' Borealis Basin, the largest depression in the northern lowlands, has mineral patterns consistent with a colossal impact, while the planet's thin northern crust aligns with models of a grazing collision. Even more provocative, recent studies of Martian meteorites found rare isotopes that resemble those in lunar samples, hinting at a long-lost exchange of material. What makes this theory revolutionary isn't just rewriting Martian geology, it reimagines the early solar system as a chaotic pinball machine. Theia wouldn't have been a lone wanderer, but one of many protoplanets ricocheting between orbits before finding their final resting places. It also suggests moon-forming impacts might be messier than we thought, with debris disks blending material from multiple worlds. Future missions could test this. Analyzing Mars' remaining northern crust for shock minerals or hunting for Theia's remnants in lunar lava tubes might uncover the truth. Until then, we're left with a haunting vision. Our younger, wetter Mars, its fate forever altered by a rogue world that would later shape our own. Roughly 54 million light-years from Earth, an astronomical riot is unfolding, one that defies every stereotype of galaxies as lonely islands in space. The Virgo cluster, our nearest gathering of over 1,000 galaxies, is a cosmic mosh pit where gravity orchestrates collisions so frequent, they've turned the entire region into a high-energy physics lab. Unlike the slow-motion mergers we see elsewhere, Virgo's galaxies are piling into one another at dizzying speeds, creating a spectacle where stars aren't just born or destroyed, they're evicted. At the heart of this chaos lies M87, the cluster's supergiant elliptical galaxy. With a monstrous black hole powering jets of plasma that stretch for thousands of light-years, M87 acts like a gravitational wrecking ball, swallowing smaller galaxies whole while flinging their stars into the abyss. Hubble Space Telescope images reveal the aftermath streams of orphan stars adrift between galaxies, their once orderly orbits shredded by close encounters. These stars aren't just homeless, they're evidence of a process called galactic cannibalism, where larger galaxies strip smaller ones down to their cores, leaving behind ghostly trails of stellar debris. But the real drama isn't just in the visible wreckage. The space between Virgo's galaxies is far from empty. It's a seething ocean of gas heated to millions of degrees by countless collisions. When galaxies plow through this medium at thousands of kilometers per second, they create shock waves that ripple across the cluster, detectable as faint X-ray glows. Chandra Observatory data shows these gas clouds aren't just hot, they're enriched with heavy elements like iron and silicon, ash from generations of supernova, blasted into intergalactic space by the violence of earlier mergers. What makes Virgo unique is the sheer scale of its bedlam. While most galaxy clusters have a dominant central galaxy, Virgo's core hosts multiple giants M87, M86, and M49, all vying for supremacy. Their gravitational tug-of-war churns the surrounding gas into turbulent whirlpools, sparking bizarre phenomena like ram pressure stripping. where spiral galaxies have their gas clouds literally torn away, leaving behind star-forming regions that dangle like beads on a cosmic necklace. Yet amid the destruction, creation thrives. The same shocks that heat the gas also trigger starbursts in surviving galaxies, their interstellar clouds compressed into glittering clusters of newborn stars. Some of these clusters are so massive, they could become independent dwarf galaxies in their own right, a reminder that even in the most violent corners of the universe, chaos and creativity are two sides of the same coin. What unfolds in Virgo today is a preview of the Milky Way's distant future, when our local group galaxies will collide in a similar frenzy. Already, telescopes are spotting stripped stars and heated gas around the Andromeda galaxy, hints that the process has begun. By studying Virgo's ongoing demolition derby, we're glimpsing the forces that will one day reshape our own cosmic neighborhood, proving that even in the vast quiet of space, no galaxy is an island forever. On June 30th, 1908, near the Podkamennaya Tunguska River in Siberia, the sky split open with a force that shook the world, literally. At 7:17 in the morning, a fireball brighter than the sun streaked across the heavens before detonating 8 kilometers above the Taiga, unleashing energy equivalent to 15 million tons of TNT. The blast flattened 80 million trees across 2,000 square kilometers, their trunks radiating outward like matchsticks in a perfect butterfly pattern. Windows shattered 600 kilometers away, and seismic stations as far as England recorded shockwaves rippling through the Earth. Yet when scientists finally reached the remote site 19 years later, they found something baffling: no crater, no fragments, just a silent forest of toppled trees and eerie, still-standing trunks stripped of branches. For over a century, the Tunguska event has defied easy explanation. Early expeditions found microscopic glass beads embedded in the soil, molten droplets of silica that hinted at an asteroid vaporizing in the atmosphere. But in 2020, analysis of fallen trees revealed a startling twist. The pattern of flattened timber matched the airburst of a stony asteroid only if it approached at an unusually shallow angle, just 30 to 35 degrees, and exploded in multiple stages. This wasn't a single detonation, but a crumbling cascade, like a cosmic boulder shattering into fragments that each blew apart milliseconds apart. The absence of a crater makes perfect sense under this scenario. Unlike the solid metallic asteroid that carved Meteor Crater in Arizona 50,000 years earlier, Tunguska's object was likely a porous, loosely packed rubble pile, asteroid, or a fragile comet nucleus, more like a flying gravel pile than a solid rock. When it hit Earth's atmosphere at 54,000 kilometers per hour, the compressive forces tore it apart violently, converting its entire mass into a superheated plasma before it could reach the ground. Newer theories add even stranger possibilities. Some researchers point to anomalies in the blast's electromagnetic effects, reports of glowing skies across Europe for nights afterward, consistent with cometary dust scattering sunlight in the upper atmosphere. Others note that the explosion's timing coincides with Earth's annual passage through the Beta Taurid meteor stream, remnants of comet in care, suggesting Tunguska might have been a chunk of that comet breaking loose. Yet the most haunting clue lies in Lake Chico, a small, oddly deep body of water 8 kilometers northwest of Ground Zero. Sediment cores show it's only about 100 years old, but sonar scans reveal no asteroid fragment at its bottom. Instead, some scientists propose the lake formed when a fridge-sized chunk of the exploding object, slowed by the initial blasts, plowed into the marshy ground like a fist into wet clay, liquefying the permafrost and leaving this scar as its only trace. What makes Tunguska terrifyingly relevant today is its scale, a reminder that city-leveling impacts aren't just ancient history. In 2013, a far smaller 20-meter asteroid exploded over Chelyabinsk, Russia, injuring 1,500 people with its shockwave. Had the Tunguska object arrived 4 hours later, it would have obliterated St. Petersburg, Current telescopes can't reliably spot such small, dark objects until they're alarmingly close, which is why NASA's DART mission and the upcoming ENEO Surveyor spacecraft are racing to improve our planetary defenses. The Tunguska event remains a cosmic whodunit, its true nature still debated in journals and conferences. But perhaps its greatest legacy is the humility it imposes, a reminder that space isn't as empty as it seems, and that sometimes the most destructive collisions leave no trace but the scars on our imagination. Hidden in the depths of our Milky Way, a band of ancient stars weaves an unusual path against the galactic backdrop, an orphaned river of starlight known as the Helmy Stream. Unlike most stars orbiting in orderly formation, these misfits move together at sharp angles, whispering secrets of a violent encounter nearly 10 billion years ago. They're the survivors of a dwarf galaxy, one no larger than the small Magellanic Cloud that dared to cross paths with our growing Milky Way, only to be torn apart in a slow-motion collision lasting millions of years. The Helmy Stream was discovered through sheer persistence. Astronomers tracking stellar motions in the late 1990s noticed something peculiar, a group of stars in the galactic halo all moving in sync, tracing elongated orbits that dipped dramatically above and below the Milky Way's plane. Chemical analysis sealed their fate. These stars carried distinct signatures, lower levels of heavy elements like iron compared to native Milky Way stars, a telltale sign they were forged in a smaller, more primitive galaxy. Today, their descendants form a vast, looping ribbon stretching tens of thousands of light years, a fossilized splash pattern from the moment their parent galaxy was shredded by tidal forces. What makes this collision so revealing is its timing. The Helmy Stream stars are among the oldest known in our galaxy, suggesting this merger happened when the Milky Way was still in its infancy, a cosmic toddler gathering building blocks. Back then, our galaxy was likely just a fraction of its current size, making the absorption of the Helmy progenitor one of its first major growth spurts. Unlike later mergers like the cataclysmic collision with the Gaia-Enceladus galaxy, the Helmy event was gentler, leaving behind a coherent stream rather than dispersing stars completely. But the Helmy Stream isn't just a relic, it's a live laboratory. The way these stars move encodes precise details about the Milky Way's gravitational field, including the invisible dark matter halo that surrounds us. Their orbits act like tracers, revealing how our galaxy's gravitational tides stretch and warp infalling objects. Recent studies even suggest the Helmy progenitor might have contributed more than just stars. Its dark matter could still be swirling in the Milky Way's outskirts, subtly altering the orbits of distant globular clusters. The most fascinating implication, the Helmy Stream hints at a universal truth: galaxies like ours didn't form in isolation. They grew by consuming smaller neighbors in a hierarchical dance that continues today. Upcoming telescopes like the Vera-C, Rubin Observatory are poised to uncover dozens more stellar streams, each a chapter in our galaxy's autobiography. So when you gaze at the night sky, remember, some of those anonymous specks of light are cosmic immigrants, bound forever to the Milky Way by the pull of a collision older than Earth itself. The Moon's scarred surface tells a violent tale, one we thought we understood. After the late heavy bombardment faded 4 billion years ago, the inner solar system was supposed to settle into relative calm. But lunar samples collected by Apollo astronauts revealed something perplexing. Certain craters and melted glass beads were far younger than they should have been, some dating to just 3 billion years ago. This wasn't just random debris, it hinted at a second wave of destruction, a resurgence of cosmic violence long after the solar system's early chaos had ended. The key to this mystery lies in a phenomenon called the lunar cataclysm, a hypothetical spike in impacts around 3.9 billion years ago. But newer evidence suggests the bombardment didn't stop there. High-resolution images from NASA's Lunar Reconnaissance Orbiter show overlapping craters, some pristine, some heavily eroded, indicating impacts occurred in distinct bursts, not a steady drizzle. One leading theory points to the breakup of a massive asteroid family in the main belt, likely triggered by a collision or gravitational nudge from Jupiter. When these fragments spiraled inward, they could have pummeled the Moon and Earth in a delayed onslaught. Imagine a cosmic game of pool where Jupiter's gravity acts as the cue stick. Computer simulations show that resonance's specific orbital rhythms, where an object's path syncs with Jupiter's, can gradually pull asteroids out of the main belt and hurl them toward the inner solar system. The Baptistina asteroid family, for example, may have been the culprit behind this late bombardment. When a 60-mile-wide parent body shattered 160 million years ago, it spawned thousands of fragments, some of which could have reached the Moon as recently as 100 million years ago. But not all scientists agree. Alternative theories suggest the Moon's clustered impacts might not reflect a true spike in asteroid activity, but rather the slow accumulation of debris from a single, earlier disruption. Others propose that tidal forces from Earth or even volcanic outgassing could have redistributed lunar material, skewing the apparent ages of certain craters. What's undeniable is that the Moon's surface is a layered archive, each crater a timestamp, each glass bead a frozen droplet from a moment of unimaginable heat. The implications stretch beyond lunar geology. If Earth endured the same bombardment, it could explain mysterious extinction events in our planet's deep past, long before dinosaurs walked the land. Some researchers even speculate that these later impacts delivered volatile elements crucial for life, like carbon and water, replenishing what the early Earth might have lost. Future missions could settle the debate by dating more lunar samples, especially from the far side, which lacks the volcanic resurfacing that complicates the near side's record. We might finally unravel the timeline of this forgotten bombardment. Until then, the Moon remains a silent witness to a cosmic assault we're only beginning to decode. On February 15, 2013, as the Sun rose over the snowy Ural Mountains, a fireball brighter than the Sun itself split the morning sky. The Chelyabinsk meteor, a 20-meter-wide asteroid roughly the size of a 6-story building, streaked into Earth's atmosphere at 69,000 kilometers per hour, releasing energy equivalent to 30 Hiroshima bombs. But what made this event historic wasn't just its destructive power. It was the sheer volume of footage captured by ordinary citizens. Thanks to Russia's widespread use of dashboard cameras, the world witnessed every frame of this cosmic spectacle, from the initial blinding flash to the apocalyptic shockwave that shattered windows across 6 cities. The footage was revolutionary for scientists. For the first time, researchers could track an asteroid's breakup in real time, counting at least 20 separate fragmentation events as the rock disintegrated under atmospheric pressure. Each explosion left a series of vapor trails that twisted in high-altitude winds, creating eerie smoke rings that lingered for hours, the most surprising detail. The meteor didn't follow a straight path. It wobbled violently as it descended, its porous structure cracking like a brittle cookie under the strain. Analysis of these wobbles revealed the asteroid was likely a rubble pile object, a loose collection of space rocks held together by weak gravity rather than a solid monolith. But the real horror unfolded minutes later. The fireball's shockwave traveled at supersonic speeds, taking nearly 3 minutes to reach the ground. When it did, buildings shook as if hit by an earthquake. Over 1,600 people were injured, not by falling debris, but by collapsing ceilings and flying glass. Security cameras captured surreal moments. Office workers thrown from their chairs by the blast, supermarket shelves collapsing under the vibration, and even a zinc factory's roof buckling inward. The damage pattern became a goldmine for researchers, helping them refine models of how airbursts propagate energy. What makes Chelyabinsk uniquely terrifying is how common such objects are. NASA estimates asteroids of this size strike Earth every 50 to 100 years, but most go unnoticed, detonating over oceans or unpopulated areas. Before 2013, astronomers had never observed an incoming meteor of this scale. Yet hours after the event, multiple satellites retrospectively spotted the asteroid in pre-impact images, hurtling toward Earth undetected. This blind spot spurred a global push for better early warning systems, culminating in projects like NASA Atlas and ESA's Fly-Eye telescopes, designed to spot incoming objects days, not hours before impact. The aftermath left physical clues too. Divers scooped up half a ton of fragments from Lake Chicxulub, including a 600-kilogram chunk that had plunged through thick ice. These dark, pebbly stones turned out to be ordinary chondrites, common asteroid material, but their sheer survival was miraculous. Most meteorites vaporize entirely during entry. The fact that these pieces reached the ground suggests the asteroid was tougher than initially thought, possibly held together by shock-absorbing veins of metal. 10 years later, Chelyabinsk remains a cautionary tale. It proved that even small asteroids can deliver city-level damage, and that our planet's atmosphere, while protective, isn't invincible. Every frame of those dashcam videos serves as a reminder. The next cosmic bullet might not give us time to blink. 8 to 10 billion years ago, long before Earth existed, the Milky Way endured a cosmic hit and run that left its structure forever changed. A dwarf galaxy, dubbed the Gaia Sausage for its stretched, elongated orbit, slammed into our young galaxy with such force that it didn't just merge. It rewrote the Milky Way's blueprint, leaving behind a thick disk of stars that still swirl around us today. This wasn't a gentle merger. When astronomers first mapped the motions of stars in our galaxy using the Gaia Space Telescope, they noticed something bizarre. A population of stars wasn't moving in orderly circles like the rest. They were hurtling on steep, plunging orbits, their paths crisscrossing the galactic center like a tangled ball of yarn. Chemical analysis revealed why. These stars were interlopers, richer in alpha elements like magnesium and poorer in iron than native Milky Way stars. They were the survivors of a dwarf galaxy that had been torn apart in the collision, their orbits frozen in time like cosmic fingerprints. The impact was catastrophic. Models suggest the Gaia Sausage was massive, roughly 500 million times the mass of our Sun, and it struck the Milky Way nearly head-on. As its stars were ripped apart by tidal forces, they didn't settle into the thin, orderly disk we see today. Instead, they scattered into a puffed-up, thick disk, a turbulent layer of stars stretching thousands of light-years above and below the galactic plane. This explains why some stars in our galaxy orbit at odd angles, their paths tilted like knocked-over spinning tops, but the collision did more than reshape orbits. It sparked a stellar baby boom. The influx of gas from the dwarf galaxy likely triggered furious waves of star formation, seeding the Milky Way with new suns. Some of these stars still shine today, their ages and compositions serving as cosmic archaeology. Others died young in supernova, enriching the galaxy with heavy elements that would later form planets and life. The most startling clue lies in the Milky Way's halo, where globular clusters, dense balls of ancient stars, orbit in sync with the sausage debris. These clusters weren't born here. They were kidnapped during the collision, dragged along like celestial trophies. Even the galaxy's central bulge might owe its boxy shape to the gravitational aftershocks of this merger. Its stars jostled into a new configuration by the impact. What's truly humbling is realizing how much of our galaxy is borrowed. The Milky Way didn't form in isolation. It grew by devouring smaller neighbors, each collision adding stars, gas, and dark matter to its structure. The Gaia Sausage was just one chapter in this violent story, but its legacy lives on in the tilted orbits of stars above us, a silent reminder that even galaxies are shaped by the crashes they survive. Of all the planets in our solar system, Uranus stands out as the cosmic oddball, not just for its pale blue hue, but for the way it spins. While most planets rotate like tops with their poles pointing roughly up and down, Uranus rolls around the Sun on its side like a bowling ball, its axis tilted a staggering 98 degrees. This bizarre orientation creates the most extreme seasons in the solar system. Imagine 21 years of continuous sunlight, followed by 21 years of unbroken darkness at each pole. For decades, astronomers scratched their heads over how such a dramatic tilt could occur. The leading theory, a cataclysmic collision with an Earth-sized protoplanet in the early chaos of the solar system, a crash so violent it literally knocked Uranus off its feet. The evidence starts with the planet's moons and rings. Unlike other gas giants where satellites orbit in tidy planes aligned with the equator, Uranus's 27 moons and 13 rings circle the planet perpendicular to its orbit, like a bullseye target spinning on its side. This arrangement is a smoking gun. If something had gently nudged Uranus over time, its moons would have resisted, staying in their original orbits. Instead, their tilted paths suggest the entire planet, along with its primordial disk of gas and dust, was yanked sideways in one traumatic event. Computer simulations paint a vivid picture, a young Uranus still surrounded by the swirling material that would become its moons, struck by an object at least twice the mass of Earth. The impactor wouldn't have just grazed the planet. It likely plowed straight into Uranus's core, delivering enough energy to flip the planet while leaving its atmosphere intact. What makes this collision particularly fascinating is the aftermath. The force of the impact would have vaporized part of Uranus's icy mantle, sending superheated water and ammonia swirling into space. Some of this material might have recondensed to form the planet's inner moons, explaining their composition of water, ice, and rock. Others speculate the collision could have locked away heat deep within Uranus, contributing to its oddly frigid upper atmosphere, nearly the coldest in the solar system despite being closer to the Sun than Neptune. The tilt also creates bizarre atmospheric phenomena. During solstices, one pole faces the Sun continuously, heating it to unexpected temperatures while the opposite hemisphere plunges into a decades-long deep freeze. This imbalance may drive Uranus's lopsided magnetic field, which is offset from its center and tilted at a 60-degree angle, another possible relic of the ancient impact. Even the planets' weather patterns seem influenced by its sideways spin, with high-altitude winds reaching 900 kilometers per hour as they scramble to redistribute heat across its skewed seasons. Yet mysteries remain. If the collision was powerful enough to tilt Uranus, why didn't it disrupt the orbits of its outer moons, which orbit much farther out? Some researchers propose a second, less violent impact later in the planet's history, subtly adjusting its final angle. Others suggest gravitational interactions with Saturn or Jupiter could have fine-tuned its tilt over millions of years. The only way to know for sure might be sending a probe to Uranus, something scientists are urging NASA to prioritize in the coming decades. For now, Uranus serves as a cosmic lesson in the violence of the early solar system. Its lopsided spin isn't just a curiosity, it's a fossilized record of a time when planets weren't yet settled in their paths, and a single collision could rewrite the destiny of an entire world. Every time we point our telescopes at its pale, tilted disk, we're glimpsing the aftermath of a crash that shaped one of the strangest planets we know. In July 1994, humanity witnessed something unprecedented, a cosmic crash in real time. Comet Shoemaker-Levy 9, a fractured string of 21 icy fragments, slammed into Jupiter with the force of 300 million atomic bombs, leaving scars larger than Earth itself on the gas giant's cloud tops. This wasn't just another celestial spectacle, it was the first time scientists watched a planetary collision unfold live, rewriting our understanding of how fragile our own planet might be in the face of such violence. The story begins a year earlier when astronomers Carolyn and Eugene Shoemaker, along with David Levy, spotted a peculiar squashed comet through their telescope. Gravitational forces from Jupiter had already torn the comet apart during a previous close encounter, stretching its remains into a cosmic conga line of debris 2 million kilometers long. Calculations revealed its fate. The fragments were locked in a death spiral, destined to plunge into Jupiter's atmosphere at 60 kilometers per second. For once, astronomers knew exactly where and when a cosmic catastrophe would strike, and the world's telescopes trained on Jupiter to document every moment. The impacts exceeded all expectations. Fragment after fragment struck Jupiter's southern hemisphere over 6 days, each explosion releasing temperatures hotter than the Sun's surface. The largest fragment, Fragment G, unleashed energy equivalent to 6 million megatons of TNT, 600 times the world's nuclear arsenal. Infrared telescopes captured fireballs soaring 3,000 kilometers above Jupiter's clouds, while Hubble imaged expanding dark smudges in the atmosphere. Soot and sulfur compounds blasted upward from depths normally hidden from view. These bruises lingered for months, some stretching 12,000 kilometers across, visual proof of Jupiter's role as the solar system's cosmic shield. But the real revelation was what Shoemaker-Levy 9 taught us about Earth's vulnerability. Before 1994, many assumed comets were fluffy snowballs that would disintegrate harmlessly in Earth's atmosphere. The Jupiter impacts proved otherwise. Even small fragments could deliver city-flattening blasts. More chillingly, the event exposed gaps in our planetary defense. At the time, only a handful of telescopes were systematically scanning for near-Earth objects. Had a similar comet been heading our way, we might not have noticed until it was too late. The legacy of Shoemaker-Levy 9 echoes in every asteroid alert today. It spurred NASA to establish the Near-Earth Object Program, leading to discoveries like the potentially hazardous asteroid Bennu. Modern simulations of asteroid deflection methods, from kinetic impactors to gravity tractors, trace their urgency back to those fiery scars on Jupiter. Even the concept of cosmic shooting galleries, where Jupiter's gravity deflects some threats toward the inner solar system while swallowing others, gained traction after this event. Perhaps most poetically, the comet's fragments carried traces of amino acids, reminding us that impacts aren't just destructive, they're delivery systems for life's ingredients. Jupiter's violent embrace of Shoemaker-Levy 9 wasn't just a spectacle. It was a wake-up call written in fire across a planetary atmosphere, urging us to look up and take note of the chaos lurking in the cosmic dark. Venus spins backward. Of all the planets in our solar system, it's the only one that rotates in the opposite direction, a slow, sluggish turn that takes 243 Earth days to complete a single day. But that's not the only oddity. Its atmosphere whips around the planet 60 times faster than the surface below, a phenomenon called superrotation, while its lack of a global magnetic field defies expectations for a world so similar in size to Earth. The answer to these mysteries might lie in a cataclysm from the distant past, a collision so violent it flipped Venus upside down and left it a planetary paradox. One leading theory suggests Venus wasn't always this way. Billions of years ago, it may have rotated like Earth, with days and nights cycling in harmony with its orbit. Then a protoplanet, perhaps as large as Mars, slammed into it at an angle, delivering a glancing blow powerful enough to reverse its spin. Computer simulations show such an impact wouldn't just slow or tilt Venus, it could literally stop the planet's rotation and send it spinning the other way like a billiard ball struck off-center. The debris from this crash might have even coalesced into a short-lived moon, later lost to tidal forces or another collision, leaving no trace behind except the planet's eerie backward motion. The aftermath of this catastrophe could explain Venus's bizarre atmosphere. The impact's energy would have vaporized vast amounts of rock, releasing enough carbon dioxide to create the planet's crushing 92-bar atmosphere, a suffocating blanket of greenhouse gases that bakes the surface at 470 degrees Celsius. Superrotation, where hurricane-force winds circle the planet every 4 Earth days, might be a lingering effect of that ancient momentum transfer, like a top wobbling long after it's been spun. Even Venus's missing magnetic field fits the puzzle. Earth's magnetism comes from its churning metallic core, but Venus's core might have been stunned into stillness by the collision. Without a rotating, conductive liquid outer core to act as a dynamo, the planet's magnetic field would have faded, leaving it exposed to the full brunt of solar winds. Over eons, this could have stripped away much of Venus's water, turning what might have once been oceans into a desiccated wasteland. Yet skeptics point to alternative explanations. Some argue gravitational interactions with the Sun, or even a long-ago resonance with Earth's orbit, could have gradually slowed and reversed Venus's spin without a cataclysmic impact. Others propose that intense atmospheric tides, dragging against the planet's surface, might have sapped its rotation over billions of years, but these theories struggle to account for the sheer extremity of Venus's backward tilt, or why its axis is almost perfectly upside down compared to the rest of the solar system. The truth might lie in future missions. NASA's upcoming Veritas orbiter and Europe's Envision probe aim to map Venus's surface in unprecedented detail, hunting for scars that could betray an ancient impact. If they find evidence of a hemispheric dichotomy like Mars's lopsided crust, or traces of a long-vanished moon in the planet's gravitational field, the collision theory could gain new traction. For now, Venus remains a cautionary tale of cosmic violence. Whether by impact or some other celestial quirk, its fate stands as a reminder that even planets aren't immune to the chaos of the cosmos. The same forces that might have given Earth its moon and tilted Uranus on its side could have turned Venus into the hostile, backward world we see today. A world where the sun rises in the west and sets in the east, and the skies themselves move faster than the ground beneath them. Omega Centauri has always stood out from the crowd. Unlike the hundreds of other globular clusters orbiting the Milky Way, tightly bound spheres of ancient stars, this one behaves like a cosmic imposter. Its stars aren't uniform in age or composition. Some are metal-rich, others metal-poor. Some orbit erratically, others in neat loops, and at 10 million stars strong, it's nearly 10 times more massive than a typical globular cluster. For centuries, astronomers assumed it was just an oddball until they pieced together the truth. Omega Centauri isn't a cluster at all. It's the fossilized heart of a devoured galaxy, stripped bare by a long-ago collision with the Milky Way. The clues start with motion. Precise measurements from the Hubble Space Telescope reveal that Omega Centauri's stars don't move in sync like a true globular cluster. Instead, they swirl in multiple directions, their orbits tangled like a ball of yarn, exactly what you'd expect if they were the last survivors of a dwarf galaxy's chaotic core. Even more telling is their chemical makeup. Most globular clusters form all their stars in one brief burst, leaving them with nearly identical compositions. But Omega Centauri's stars vary wildly, with some containing 50 times more heavy elements than others. This isn't just a cluster, it's a graveyard of multiple stellar generations, each born from gas enriched by the explosions of earlier stars, a hallmark of galaxies, not clusters. The smoking gun came when astronomers mapped the cluster's center. Hidden among its millions of stars lurks a mysterious dark mass, possibly the remnant of a supermassive black hole, the kind only full-fledged galaxies possess. This phantom gravitational anchor weighs in at 40,000 solar masses, its presence betrayed by the way nearby stars whip around it at dizzying speeds. No ordinary globular cluster has such a beast, but a devoured galaxy's core, that's a different story. So how did this galactic nucleus end up orbiting the Milky Way intact? Simulations suggest the original galaxy, dubbed the Omega Centauri progenitor, was likely a dwarf spheroidal, perhaps 1/10 the Milky Way size. When it ventured too close billions of years ago, our galaxy's tidal forces shredded its outer layers, scattering stars into the halo while the dense core resisted dissolution. Today, those orphan stars form a vast, faint stream arcing across the southern sky, a ghostly trail leading back to their doomed parent. The collision's timing remains hotly debated. Some argue it happened more than 10 billion years ago when the Milky Way was still assembling itself. Others point to younger, metal-rich stars in Omega Centauri as evidence of a more recent merger, perhaps within the last 5 billion years. Either way, the cluster's survival offers a rare glimpse into the Milky Way's violent growth spurt, one cannibalized galaxy at a time. What makes Omega Centauri truly special is its living history. Every star in its core is a witness to that ancient collision, their motions frozen in celestial amber. By studying them, we're not just reconstructing a single event, we're reading the autobiography of our galaxy, written in starlight and gravity. And somewhere out there, another Omega Centauri may be waiting, its stars already falling toward us in a dance that won't end for billions of years. 467 million years ago, Earth endured a celestial hailstorm unlike anything seen since. The cause, a massive asteroid collision far out in the belt between Mars and Jupiter, shattering a 150-kilometer-wide parent body into fragments that spiraled inward toward the inner solar system. For millions of years, debris rained down on our planet, not as city-leveling impacts but as a relentless drizzle of smaller meteorites, their remnants now embedded in ancient seafloors from Sweden to China. But here's the twist: this bombardment didn't trigger a mass extinction. Instead, it coincided with one of the most dramatic explosions of biodiversity in Earth's history, the Great Ordovician Biodiversification Event. The smoking gun lies in fossilized meteorites called chromite grains. Drill cores from ancient limestone reveal layers packed with these microscopic minerals, their chemical fingerprints tracing back to a single asteroid family. Unlike the iridium layer marking the dinosaur-killing Chicxulub impact, this isn't a thin line, it's a band spanning millions of years, evidence of prolonged bombardment. But the real revelation came when scientists matched these grains to a specific asteroid type, L chondrites, the shattered remnants of which still litter Earth today as common meteorites. The timing aligns perfectly with radioisotope dates from asteroid debris in Swedish quarries 467 million years old, give or take a million. What makes this collision extraordinary is its paradoxical effect on life. As meteorite dust filtered through the atmosphere, it likely dimmed sunlight just enough to cool the planet slightly, not a catastrophic winter, but a gentle nudge toward more temperate climates. Simultaneously, the bombardment delivered phosphorus and other nutrients to the oceans via dissolving meteoritic material, fertilizing marine ecosystems. The result, a burst of evolutionary innovation. Trilobites diversified into dozens of new forms, jawless fish developed armored plates, and the first coral reefs began stitching together, laying the foundation for modern marine ecosystems. The mechanism behind this renaissance might lie in disruption. Before the bombardment, Earth's oceans were stable but stagnant, dominated by a few well-adapted species. The meteor shower acted like a cosmic reset button, creating fluctuating conditions that favored generalists over specialists. New niches opened as temperatures shifted and nutrient flows changed, opportunities seized upon by adaptable creatures. It's a pattern seen in miniature after volcanic eruptions or landslides. Temporary chaos breeds long-term diversity, yet the Ordovician meteor shower wasn't entirely benign. Some evidence suggests it may have triggered localized extinctions among species unable to adapt, particularly in shallow seas where debris settled thickest. This subtle pruning of the evolutionary tree, removing some branches while encouraging others to flourish, highlights nature's delicate balance between destruction and creation. Today, the event serves as a haunting counterpoint to later mass extinctions. Unlike the apocalyptic Chicxulub impact, which stamped out 75% of species in a geological instant, the Ordovician bombardment was a slow burn, a reminder that cosmic violence doesn't always end in catastrophe. Sometimes it's the pebbles, not the boulders, that shape the course of life, and sometimes the universe's most violent acts are the ones that give life its greatest chances to thrive. Right now, as you read these words, our solar system is adrift in a vast cosmic cavity, a 300 light-year wide local bubble sculpted by the violent deaths of massive stars. This isn't some abstract region of space, it's our galactic neighborhood, a celestial clearing where the interstellar medium is thinner and hotter than the surrounding galaxy. And its origin story reads like a chain reaction of stellar detonations, each supernova explosion pushing gas outward like a cosmic snowplow, carving the bubble we call home. Around 15 million years ago, a cluster of young, massive stars dozens of times heavier than our Sun formed in this region. These stellar behemoths lived fast and died young, exploding as supernova within just a few million years. Each detonation sent shockwaves rippling through space, compressing nearby gas into new stars while simultaneously blowing a growing cavity in the interstellar medium. Over time, these overlapping explosions created the local bubble's delicate structure, a porous, irregular shell of cool gas and dust surrounding a hot, diffuse interior where temperatures soar to 1,000,000 degrees. What makes this bubble so critical isn't just its emptiness, it's the protection it offers. The local bubble's thin, supernova-heated plasma acts as a natural filter for galactic cosmic rays, high-energy particles that would otherwise bombard Earth at much higher intensities. Without this buffer, our planet's magnetic field and atmosphere would face a constant onslaught, potentially altering climate patterns or even influencing the evolution of life. Even now, spacecraft like Voyager, poised at the bubble's edge, detect a steep drop in cosmic ray counts inside its boundaries, a testament to its shielding effect. But the local bubble isn't static. Our solar system just happened to drift into it about 5 million years ago, and we're currently passing through a particularly sparse region near its center. Maps of nearby stars reveal something astonishing. Many of the brightest stars in our night sky, like those in the Scorpius-Centaurus association, sit along the bubble's expanding rim. These stars owe their birth to the same shock waves that forged the cavity, their formation triggered by supernova compressed gas. The bubble's influence extends beyond astronomy. Astronauts on future deep space missions will need to account for its structure when planning radiation exposure, as leaving its relative safety could mean venturing into a far more particle-rich environment. Even Earth's climate history might bear its fingerprints. Some researchers speculate that past shifts in cosmic ray flux, modulated by the bubble's changing density, could have subtly influenced cloud formation and solar absorption. Yet the local bubble is just one of many such structures in our galaxy. Like froth on an ocean, the Milky Way is filled with similar cavities, each the footprint of long-dead stars. Their overlapping walls create a sponge-like interstellar medium, with stars and planets huddled in the voids between. One day, the bubble will dissipate, its energy fading into the galactic background. But for now, it remains a silent, invisible guardian. A reminder that even the emptiest corners of space are shaped by ancient collisions we're only beginning to understand. Our solar system may seem like a stable cosmic clockwork today, but its future is written in collisions yet to come. Take Mercury, the smallest planet harbors the most chaotic destiny. Right now, its lopsided orbit brings it perilously close to the Sun's gravitational grip. And within the next 5 billion years, simulations suggest a 1% chance it could veer wildly off course. Picture this: Mercury's path destabilizing so dramatically that it crosses Venus's orbit, triggering a catastrophic game of gravitational pinball. One model even shows Mercury colliding with Venus in 3.3 billion years, or worse, getting flung into the Sun or ejected from the solar system entirely. And that's just the beginning. The Sun's death throes will rewrite the rules entirely. As it expands into a red giant 7.5 billion years from now, swallowing Mercury and Venus whole, Earth won't escape unscathed. While our planet might avoid total annihilation, the Sun's bloated outer layers will scrape against it, boiling away oceans and stripping the atmosphere into space. Meanwhile, the outer solar system will become a demolition derby. Jupiter's gravity could fling Mars into a wider orbit or slingshot it toward Earth in a slow motion near miss. The asteroid belt, stirred by the Sun's dying winds, might send debris careening into gas giants, sparking new rings or igniting brief, fiery storms in their atmospheres. But the real chaos begins after the Sun sheds its outer layers, leaving behind a cooling white dwarf. Freed from the Sun's steadying influence, the remaining planets will drift like ships unmoored. Over trillions of years, gravitational nudges from passing stars will perturb their orbits until collisions become inevitable. Imagine Neptune and Uranus, their orbits decaying until they graze each other, merging into an icy superplanet. Or Jupiter, its gravity weakened by eons of stolen mass, finally surrendering to a fatal embrace with Saturn. The solar system's final act lies in the grasp of the Milky Way's supermassive black hole, Sagittarius A. In 10 to the 26th years, a time span so vast it dwarfs the current age of the universe, our white dwarf Sun will finally spiral into the galactic core. There, it won't so much collide as dissolve, its atoms stretched into spaghetti like streams by tidal forces, joining the black hole's accretion disk in a silent, dark finale. Yet even this isn't truly the end. Quantum mechanics hints that black holes themselves evaporate over time, meaning our solar system's matter might one day escape as faint Hawking radiation, a whisper of atoms that once formed worlds, scattered back into the cosmos to begin the cycle anew. Every collision, from Mercury's first misstep to the Sun's final plunge, is just a step in the universe's endless dance of destruction and rebirth. From the Big Bang's primordial fireball to the bullet-like remnants of shattered asteroids still raining down on Earth today, these 25 cosmic collisions paint a universe far from serene, a place where chaos isn't the exception but the rule. Every crater, every tilted planet, every stream of orphaned stars tells the same story. Creation thrives on catastrophe. The atoms in your body, the moon in our sky, even the very shape of our galaxy, all were forged in moments of unimaginable violence where destruction and rebirth are two sides of the same coin. Humanity stands at a unique crossroads in this grand saga. For the first time in 4.5 billion years, a species has evolved with the ability to witness these collisions not just in hindsight but in real time. Telescopes now track near-Earth asteroids with precision, while supercomputer simulations reconstruct galactic mergers down to the last stellar orbit. We've even taken our first tentative steps toward planetary defense, with missions like DART proving we might one day nudge a threatening asteroid off course. Yet for all our progress, we're still newcomers to this cosmic arena. The universe has spent eons perfecting its art of collision. We've barely begun to read its brushstrokes. What comes next? The Milky Way's inevitable merger with Andromeda looms 4 billion years in the future, but closer threats whisper in the darkness. Will a rogue interstellar asteroid hurled from some distant star system cross our path unexpectedly? Could Jupiter's restless gravity fling a dormant comet toward the inner solar system, as it has countless times before? Or might we discover that dark matter, the universe's invisible architect, has been steering unseen catastrophes all along? The most humbling realization isn't just that collisions shaped our past, it's that they'll define our future. Whether we're here to witness them or not, the universe will keep rewriting itself in explosions and impacts long after our sun flickers out. So tell us, what do you think the next great cosmic collision will be? A supernova visible in broad daylight, a rogue black hole slipping unnoticed through our solar system, or something beyond our current imagination? Share your theories below, because in a universe built on chaos, the only certainty is that the next impact is already on its way.